Okay, so I think a lot of that is quite intuitive, and I've got about 10 minutes, so I better move on. I'd like to end up with monitoring applications. What does LiDAR monitor? Well, it monitors the surface. What surfaces change in hydrology? Snowpack surfaces, glacial ice surfaces, water levels. So these are intuitively the three things that we could utilize LiDAR to monitor. I'm not really going to talk too much about how practical it is to utilize LiDAR for monitoring, but we will touch on that with regards to the snow application, because I do think there is some operational possibilities there. As I earlier mentioned, we've done some proof of concept studies with snowpack mapping, most recently in the Rockies in Kananaskis and Elbow Creek, although what I'm illustrating here is Marmot Creek, just near the ski hill in Kananaskis. So this is just the hillshade of that watershed. Here we can see a snow depth model. So what we're seeing here is the difference between the data set collected in the summer, August of 2007 and late March 2008. So there's over a year between them, but that's the time difference. So summer 2007, pretty much void of snow. March 2008, very, very thin snow year. Not a good time to be doing this study, but we planned it. We got everything ready. We were there. We didn't have a lot of choice. Based on historical records, we thought, well, at the end of March, beginning of April is probably a good time to do this. But that year just wasn't particularly good. Anyway, we got out of it what we hoped to get out of it. It would have just been nice to see a little bit more snow. So anyway, you can kind of see the distribution of snowpack across there. Now, I'm not going to pretend it's perfect, and I'll show you some illustrations about why that is, but we do see the macro scale properties of snow distribution. So for example, in the gullies, in the upper reaches of the alpine, they're filled with snow, up to depths of 3 and 4 meters in some cases. And treeline. Treeline is where we see the highest accumulation of snow, and I'm going to come back to that in a little while. And then throughout this forested area, we do see a general increase in snowpack depth from the valley all the way up towards, just below tree line. I mean, just below tree line, we're seeing the highest depth accumulations. But you'll also notice, like, there's a huge amount of heterogeneity in that snowpack. I mean, we know that snowpack in these environments is very heterogeneous anyway, but now we can start to map it in quite a lot of detail. So for the sake of interest and correlation, we can map some of the other attributes. Here we're looking at the signal intensity, and the signal intensity is influenced by a number of factors, snow being one of them, of course. We can see we're getting bright reflections off snow just above tree line. We lose that brightness as soon as we go into the forested area, because in the forested area, those pulses are being split. So we're seeing lower intensities because there's no single surface reflecting with a high response. But here we see clearings. In the clearings we've got snow, and we can see high intensity. Terrain elevation. And here we see canopy fractional cover. So again, those clearings come out as being really obvious. Tree line comes out as being really obvious. And we've got some selective thinning going on in there that we can see. Okay, so I said I'd illustrate some of the validation data. Up in the alpine, we actually get very good correspondence between field data, field snow depth measurements, and the LiDAR differences. And so that's quite encouraging. There's, I think, 2 reasons for that. One, the distance between the aircraft and the survey area is at its minimum in the alpine zone. So the propagation of errors is minimized at the highest points in a terrain surface. So that's one element. The other element is there's no forest in the way. There's no trees that are confounding those or interfering with those laser pulses. So we're not introducing noise as a result of weaker signals or other objects in the optical path. Now when we get down into the valley, in this particular situation, the valley is sometimes open, sometimes forested, but generally more flat. Now when we're on flat surfaces, again, we're not propagating terrain-based errors, but when we're on steeply sloped surfaces, we're also propagating a terrain-based error, the kind of thing Tristan was talking about yesterday. So Flatter areas, the data are not so bad, but very widely distributed because we've got variable influences of vegetation in the valley, and we're as far away from the sensor as we possibly could be. So again, errors are propagated in that situation. Now, and all of these are taken in the forest on the hill slopes. So we've got a number of influences here. Forest cover related, so maybe very weak returns, interfered returns, and slope effects. And we can't really separate out all of those effects. It's difficult to isolate them. And so that's kind of what we're seeing. But the encouraging thing is, overall, the depths are kind of the right order of magnitude. They're all kind of in the ballpark. There's obviously some bias here, upwards bias at the low end in the forested area, and I think that's probably mostly a result of ground level vegetation influences below the snowpack from the summertime data set. When we summarize the depth profiles with hypsometry, what we see is, let's look at this. So the black line represents the basin hypsometry, or the change in area with vertical elevation. The blue represents the same metric but for snow cover. So we see maximum snow cover, or rather there's a bimodal distribution of snow cover. So we've got two peaks, one at this elevation and one at this elevation, in terms of the aerial coverage. And now if we look at it in terms of snow volume, we see the peak snow volume occurs right here. It doesn't occur up top, it occurs right here. Now if we look at tree line is kind of dropping through this peak snowpack area. So what that tells us then is that the peak snowpack accumulation potential occurs at tree line, just above and just below. So that's a very important area within our watershed. And now we may have known that already, but the really neat thing is we've quantified snow volume across that entire watershed and across that entire hypsometric grade. So if we've got another watershed adjacent to it, and we know the watershed hypsometry nearby, and we know what the tree line properties are nearby, we can take this information and apply it to another watershed based on its hypsometry and tree cover characteristics. And so what we did in another parallel study was applied a sampling approach, where we distributed the landscape. In this case, this is the Elbow Creek watershed upstream of Calgary. We distributed that landscape into what we considered our snowpack accumulation units, kind of analogous to a hydrological response unit, and that was based on elevation, aspect, and canopy openness. We found that those are the three most sensitive attributes. And then we sampled snowpack from the LiDAR in each one of those three strata, and we used that information from the sampling transects to then apply the results across the entire Elbow Creek watershed. And so that's what we came up with was a snow depth map. And so from that snow depth map, we calculate a volume of snow. And now if we have a snow water equivalence or snow density measurement, then we can apply that density measurement and get SWE. Now of course LiDAR is not going to give us SWE, LiDAR is not going to give us density, so we still need that extra measurement. I'm going to wrap this up quite quickly, but let's look at glaciers for a minute. We've been fortunate in that the Paedo Glacier at the end of the icefield, in between Banff and Jasper, has been studied quite extensively. We've got DEMs going back to 1949. So here we've integrated the photo-based DEMs with LiDAR DEMs, which we've captured from 2000, 2002, 2006, 2007, 2010, 2013. We've done LiDAR for all of those. And so we've been able to put them together to measure at some fine level of detail what the changes are. Unfortunately, I haven't yet put the 2013 into this mix because it's still quite fresh and I just haven't had the time yet. But you can you can see the down wasting in these areas and the patterns of down wasting. So it's a nice visual. But I think what's more interesting is that we can also track changes in the geomorphology of the landscape. So what we're seeing here is as the glacier recedes, and we can see that pattern of recession, we can also see the hill slopes surrounding and starting to collapse into it. And we know that this area is actually very much ice cored. We know that this area is also ice cored. As the glacier recedes, there's kind of overturning at the sides, the debris falls onto the ice gets insulated, ice gets entrained, and then it's stored there. You've got these big honking ice cubes on the side of the slopes that are just stored for years and years and years, potentially a century or more. We don't really know exactly how long they're stored there. But the point is, as these glaciers recede, these areas of buried ice remain, and they're still contributing to runoff and base flow, even when the glacial flow could potentially have ended. Anyway, so the idea is that with if we look at a couple of cross sections through the LiDAR data in that area I just illustrated, we can see the down wasting of the moraines, we can see the lateral motion of the moraines, we can calculate the volumes of wastage from the slope, we can observe whether or not there's any deposition at the foot of the slope, and we can use all of this information to infer that most likely what we're seeing is ice core ablation in here, as well as geomorphic movement processes. So this allows us to look inside the ground in a way and try and start to measure volumes of ice core change, as well as the obvious glacial change. There's just one thing I wanted to end on, was the idea of using LiDAR for water levels. You know what, I'm not going to pretend this is something I'm going to do operationally anytime soon, because LiDAR is still pretty expensive, at least from the point of view of going out and monitoring water levels. But I just wanted to illustrate that you can do it. Here we have some data collections over the McKenzie Delta, and we've got profile lines along these river channels. And here's the LiDAR point cloud information extracted along those river channel profiles. Here we've got a step because the aircraft went away, came back and flew it at a different time. And this is a very dynamic environment. We've got tidal influences, we've got changes in runoff, of course. But the neat thing is we've got gradients now down these channels. And if you take the hydrometric network is not sufficient to tell you what the hydraulic gradient is on those channels. So now we have information on the hydraulic gradients along those channels. We also have information on the water level variations across the McKenzie Delta. So here's all of the channels that we've crossed if you do a cross section across the delta, many channels. And so here we're looking from one end of the drainage, the delta, all the way down to the other. And the delta's around about the size of the Bay of Fundy. Well, we're in Alberta, that's probably not a good frame of reference.
I understand it.
I do.
Well, that's good that some people... The Bay of Fundy is pretty big, right? I couldn't tell you exactly what it is, but there's at least 100 kilometers between one end and the other. And so what we can see is the difference in water level from one end to the other of the delta. And we can see how at one end of the delta, the water level looks like this. But then as you're moving downstream towards the ocean, it's kind of like doing this. I don't know, yeah, it's something like that. I don't know if I've illustrated that correctly, but that's kind of what those illustrate. So that tells us something about the dynamics of that landscape. Okay, it's the dynamics for a snapshot in time, but we would never have known that. We would never have known that the runoff through the delta has this kind of characteristic, kind of wave to it. And we haven't really... We've published that, but we haven't really explored what we could fully do with that yet, and I'm hoping someone will do some hydraulic modelling with it. Here's another little hydrological or hydraulic oddity that we discovered. Here are flight lines, these, or where the flight strips were across this channel. Now if we look at the points A, B, C, D, E, and then we look at the points A, B, C, D, E on this river channel profile, we'll see here at the water level starts at around 1 meter, increases up to about 1.1 meter, then drops to about 0.9 meters. When I first saw that, I thought, oh, the data's got to be junk. There's got to be some kind of discrepancy there. But then when we looked into it further and further, there was no way that there was a discrepancy there, because when you look at the data in the off-water areas, everything aligns really well. And so we can only conclude that C and D at this point here, as the flow constricts and goes into this bend and eddies are formed here, the water actually rises up by about 10 centimeters. And you would not be able to characterize that unless you put in a lot of stream gauges all the way around that bend. And who's going to do that? It's very expensive to put stream gauges, in such a large channel like that. So this tells us something about the momentum that is impacting, or the energy that's impacting this stream bank. And of course, you've got a clavic here, which is a town site. So you've got active erosion on that, the edge of that stream bend, and there's a lot of force going in there. And we could quantify that by the amount of energy contained within that bulge. We could actually, from this, we could determine how much energy is contained as a result of that bulge in the water level. So that's interesting. Again, it's something we haven't fully exploited. It's just a little interesting oddity that we came across, and I think does warrant a little bit more exploration. Although really we need to get out in the field, and that isn't so easy. Okay, so we can do LiDAR water masks. We looked at that yesterday. And we can put a lot of this information together to map water levels across the landscape. Okay, we can do that, but I'm not going to pretend that's something we're going to do operationally anytime soon. And we can calculate water volumes.